In the last couple of lectures, we've laid out the procedure for statistical hypothesis testing. Now we're actually going to put that procedure into action with some examples. In section 9.5, we deal with the three different scenarios that I'm going to ask you to be familiar with, and we're going to break the lectures up so that we're dealing with one scenario at a time. In this video, we're going to talk about hypothesis testing for proportions, and the calculator function we use for that is called 1PropZTest. 1prop for one proportion, z because we're going to be using the normal approximation to the binomial distribution, and test instead of int because it's a hypothesis test, not a confidence interval. My advice is for you to follow a 6-step procedure as you do each hypothesis test. And so what I'm going to do is introduce you to the procedure in this particular video, and then I'm going to point out the specifics for our 1PropZTest as we go through. Here's the general process that I would suggest that you follow. Step 1, you need to determine the hypotheses. Whether you're doing this in real life or just doing a practice problem in a classroom, you have to have hypotheses to work off of in order to conduct a hypothesis test. There will be a null hypothesis and an alternative hypothesis, and again in a moment I'll point out specifically what those will look like when you're doing a hypothesis test for a proportion. Let's walk through the entire procedure first. Secondly, you're going to identify the level of significance, which we denote by alpha. This is the probability of a type 1 error. In the real world, you would choose this on your own, and most commonly you would use 5%, 0.05. In a classroom setting, the value of alpha will almost always be given in the problem. Third, you collect the sample evidence. The evidence you have is dependent on the scenario where you're in, and again, I'll get back to what it is for proportions in a minute. Once you have the sample data, you compute the p-value based on, remember to compute the p-value, we pretend like the null hypothesis is true, and then we basically ask, what is the probability that a random sample could give us statistics as extreme as what we witnessed if the null hypothesis was true? That's how we get our p-value. This is where the calculator function comes in. It's going to take over and do that p-value for us. We won't have to go through the steps ourselves. Then you make a decision about the null hypothesis to either reject or fail to reject. We'll review when you do each here in a moment. And then you'll write a conclusion, and that conclusion should address the claim that's made in the problem. You'll notice that most of the time we're going to be writing about the alternative hypothesis in the conclusion, and that's because, in my opinion, we've already said everything we need to say about the null hypothesis in the decision. The conclusion will be written in a way that people who don't have a deep statistics understanding will still be able to follow it. The decision's going to sound kind of nerdy. The conclusion's going to be more plainly written. Okay, back through the steps. But this time I want to point out what that will look like in our scenario. So in this section, we're going to be doing hypothesis testing for a proportion. So in step 1, when you determine the hypotheses, you're going to have a null hypothesis and an alternative hypothesis that are both for proportions. The null hypothesis will be some claim that the proportion p is equal to some number, and I'm going to use what's going to look like a weird notation for that number. I'm going to call it p sub 0, and I'm not doing that to be extra nerdy. That's the notation your calculator is going to use, so I want you to get accustomed to seeing that. So the null hypothesis will be the claim that p is equal to some number p sub 0, and that p sub 0 has to be between 0 and 1. You would never have a hypothesis that the proportion was equal to 0 or equal to 1, so our p sub 0 is going to be between 0 and 1. The alternative hypothesis has to somehow contradict that, and there are 3 ways that we could contradict that. We could contradict that by saying that p is not equal to p sub 0, that it's somehow different, that p is less than p sub 0, or that p is greater than p sub 0. And the way that you know which one to choose is based on the wording in the problem. You'll usually see the alternative hypothesis given as a claim in the problem. If you're ever doing a problem where they don't explicitly state the alternative hypothesis, the safe play is to use the not equal to option. Oftentimes, though, the problem will kind of point you in the right direction, which inequality you should use. Secondly, you identify the level of significance, which we call alpha. In a practice problem, this is just finding that value of alpha in the problem somewhere. Sometimes they use the words level of significance or significance level. Sometimes they use the symbol alpha, but you just have to make sure you know it. I ask my students to do this early on in the process to make sure that you're really doing a hypothesis test and not some other type of problem. So look for that value of alpha. Make sure you know that there's a level of significance in the problem. Step 3 is to collect the sample evidence. For a proportion, the sample evidence is the number of observed successes, which we call x, and the sample size, which we call n. The sample evidence is used to calculate the sample proportion, which we use in turn to find the p-value. To find the p-value in this scenario, we use the calculator function 1PropZTest. And in this video, that's what we're going to focus on. We're only going to be using that calculator function. Once we've got the p-value, you make the decision. Here are those two rules. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is small, then the null hypothesis is not very believable, and so we're going to reject it. And what do we consider small? Smaller than alpha is small. If the p-value is smaller than alpha, then we're comfortable rejecting the null hypothesis. If the p-value is greater than alpha, then we can't reject the null hypothesis. The way I like to say it is we fail to reject the null hypothesis. There was some evidence indicating that the null hypothesis was false, but it wasn't strong enough for us to go out on a limb and declare that we believe that it's false. So we failed to reject it. Now the calculator won't do this part for you. It doesn't take alpha as an input, so you're going to have to remember to apply this rule. And I've made up a mnemonic for this. It's not a real word, but it sounds like it is. I tell my students to remember PILTAR. P is less than alpha reject. PILTAR. P is less than alpha reject. I know it's not a word, but it sounds like a word. As an aside, you don't need a second rule. If you don't reject, then you fail to reject. And besides, P is greater than alpha, fail to reject. Pig-tafter doesn't really roll off the tongue like PILTAR. If you want to use pig-tafter as your rule, you can, but I'm going to use PILTAR. P is less than alpha, reject. And then I want you to write a fairly plain language conclusion. I want you to write an interpretation of our decision that addresses the claim and the problem. And we'll talk about that as we do specific examples. Let's jump into an example. Around 47% of Americans have fallen victim to porch pirates, people who steal packages from their front door. Do security cameras deter these thieves? Suppose a random sample of 60 homeowners who use security cameras is gathered. In this sample, 18 of them had a package stolen from them. Does this data provide enough evidence to support the claim that less than 47% of homeowners with security cameras have had a package stolen from their front door? Let alpha equal 0.01. First, how do we identify that this is a hypothesis test question at all, and not, say, a confidence interval or maybe even a different type of problem from an earlier unit? We're being asked to see if we can support a claim, so we're testing a claim. Furthermore, we're given a significance level, and so that significance level is going to be applied in the hypothesis test. Because we're being asked to test a claim, we're going to go through our 6-step process. So step 1 is to determine the hypotheses. We're going to have a null hypothesis, which we denote by H sub 0, and an alternative hypothesis, which we denote by H sub A. Let's go into the problem and see what the claim is. They only mention one of them, actually. Does this data provide enough evidence to support the claim that less than 47% of homeowners with security cameras have had a package stolen from their front door? The proportion is less than 47%, 0.47. Now, which hypothesis is that? It doesn't say in the problem, but we know because of our rules. The null hypothesis always has an equal sign in it. The alternative hypothesis is the one with the inequality, and so the claim that P is less than 0.47 must be the alternative hypothesis. The null hypothesis is always a statement of equality, and notice that in our nerdy notation, the number that we use in each hypothesis is the same. So if you know the alternative hypothesis, the null hypothesis is easy to come up with. It has the same parameter and the same number, but it's a statement of equality rather than an inequality. So the null hypothesis is the claim that P equals 0.47, and the alternative hypothesis is the claim that P is less than 0.47. The null hypothesis is basically saying that there's really no difference whether you have a security camera or not when it comes to having stuff stolen from your porch. The alternative hypothesis disagrees with that and says no, the proportion of Americans with security cameras who have things stolen from their porch is actually less than what it is for the general population. So those are our two claims in this problem. Once you've got your hypotheses, I want you to dig up the level of significance, which we call alpha. In this problem, we've already looked at it. We used it as a reason to know that this was a hypothesis test. Alpha is set to 0.01. I would just note that somewhere. Alpha is 1%. We use that in the 5th step to make the decision, but I want you to look for it early on to make sure you're actually doing a hypothesis test and not some other type of problem. Step 3, we collect the sample evidence. When you're doing a hypothesis test for a proportion, you need the number of observed successes and the sample size. We were told that there was a random sample of 60 homeowners, so N is 60. And in that sample, 18 of them had a package stolen from them. Now, I know that doesn't sound like a good thing, so calling that a success sounds weird. But remember, a success isn't a good, joyful, happy thing. A success is just the outcome that you are interested in. And we're talking about homeowners with security cameras who've had packages stolen, so stolen packages would be a success. So there are 18 successes. So X is 18, N is 60. Now here's where the probability comes in. 18 out of 60 is much smaller than 47%. Some of you can probably see that that reduces to 3/10. And so that's only 30%. 30% is much smaller than 47%. But the question is this data statistically significant? That is, can we extrapolate from this that the proportion of all homeowners with security cameras who've had something stolen is less than 47%, is less than the general population? Clearly it's true in the sample, but we want to know if we can take the leap to say that for the entire population. And that's where the probability comes in. We couldn't possibly track down every homeowner with a security camera, so we've randomly identified 60 of them, got data from them, and now we're asking if that data is statistically significant enough for us to make the same claim about the entire population. That's really what we're doing here. The process we're using is to compute the p-value in order to do that. And the p-value is found by using the 1PropZTest calculator function. So let me show you how to access that. You press Stat and you scroll to Tests, and 1PropZTest is choice 5. I'm going to press choice 5. The first input you'll see is p sub 0, and that's why I used that ridiculous notation when we were talking about the steps. That's the same notation that your calculator uses. So the first input to the calculator is the number in your hypotheses. In our example, that number is 0.47. So p sub 0 is 0.47. X is the number of observed successes. We said there were 18. N is the sample size, which is 60. And then this next choice allows you to select the symbol in your alternative hypothesis. Remember, the alternative hypothesis could have one of 3 inequality symbols, so the calculator is letting us choose the correct one here. In our problem, we're testing the claim that the population proportion is less than 47%, and so we want to choose the less than symbol, which is the second option here. This now says the population proportion is less than p sub 0, which is 0.47. That's the claim that we made. And now you have the option to calculate or draw. If you draw, you'll see the normal approximation to the binomial distribution and how the calculator found it under the curve. We're just going to use the calculate option. Hit enter on calculate, and you'll get this massive output screen. The first thing you'll see is the name of the test. This is becoming more and more important that you've used the right calculator function. We're up to 4 so far, and by the time the unit is over, we'll have 7. So make sure you use the right calculator function. Next, you should see something equivalent to your alternative hypothesis. The proportion is less than 0.47. That's what our alternative hypothesis said, so that looks good. This next line is called the test statistic, and if we were doing this by hand, that's the number that we'd have to look up in the tables. We don't really need that though, because we're doing a p-value approach, so we're going to look at the next line. This can be confusing because it looks like there are 2 p's here, but this line directly underneath the z, that's the p-value. It's around 0.004. I know it has a lot more decimal places than that, but rounding it to 0.004 allows me to easily compare it with alpha. The thing underneath that isn't a p-value, it's p-hat. You can see the 3 little pixels on top of that. That's that 30% that I mentioned. 30% of the sample was a success. And then underneath that you see the sample size. I guess you could use that to check to make sure that you typed in the correct value of n. But we really only needed the calculator for the p-value because that's what we're going to use to make our decision. Go back to our steps. If the p-value is less than or equal to the value of alpha, then we reject the null hypothesis. And if the p-value is greater than alpha, then we fail to reject the null hypothesis. Well, 0.004 is smaller than 0.01. The p-value is less than alpha. We reject the null hypothesis in that case. we're pretty sure the null hypothesis is false. Basically, the p-value is telling us that if the null hypothesis was true, then the probability that we could have witnessed something as extreme as what we saw is only about 0.004, which is around 1 in every 250 samples. It would be very unlikely to gather data like this if the null hypothesis was true. And so we don't believe the null hypothesis. This is that rare event rule. We're going to reject the null hypothesis. If we reject the null hypothesis, then we're going to support the alternative claim. Basically, we're saying that we're pretty sure the null hypothesis is false because the sample data leans so heavily in the direction of the alternative hypothesis. And so we're going to support the alternative hypothesis. When you reject the null hypothesis, you're going to support the alternative hypothesis. And that's how we're going to write our sentence. We're going to say there is, and I'm plain here and I just say enough evidence. There are fancier ways to say it. A lot of textbooks will tell you to say there is sufficient evidence. If you really want to nerd it up, you'll say there is statistically significant evidence. I avoid that wording because I'm trying to keep my interpretation plain on purpose. So I'm just going to use the word enough. There is enough evidence to what? Well, we're going to support the claim made by the alternative hypothesis. So to support the claim that, now I just look up the claim. What claim did we have? Well, in symbols, it's p is less than 0.47, but that's not very specific to the problem. So let's go back to the wording. The claim that we were trying to support was that less than 47% of homeowners with security cameras have had a package stolen from their front door. Let's write that. There is enough evidence to support the claim that less than 47% of homeowners with a security camera have had a package stolen from their front door. In other words, it appears based on our sample data that having a security camera makes you less susceptible to having a package stolen. And perhaps that claim seems obvious, that having a camera will make it less likely that somebody would steal from you. But you can't really make a claim like that unless you have statistical evidence to support it, and so now we have it. Let's try another example. A study conducted by Sleepopolis shows that 34% of all adults go to bed with a comfort item, such as a stuffed animal or a blanket, something like that. Researchers suspect that the percentage is higher for college students. Perhaps they suspect that simply because college students would be on the younger side of the adult population, right? They're less removed from their childhood and maybe they still have an attachment to something to help them sleep. But this is the claim. So now they're going to test it. Suppose a random sample of 50 college students contains 21 who use a comfort item to help them fall asleep. Using a significance level of 0.10, test the claim that the percentage of college students who go to bed with their comfort item is greater than 34%. Now 21 out of 50 is 42%. That's bigger than 34%. But the question is that difference statistically significant? That is, can we then jump to the conclusion that more than 34% of all college students use one of these comfort items? If your knee-jerk reaction is to say that that sample size is too small, I want to remind you that in the previous example, our sample size was only 60 and we still got a really small p-value. So you can't just base it on the sample size and say it's not statistically significant, just like you can't just say 42% is more than 34%, so it is statistically significant. We have to put all of those pieces together using our knowledge of probability distributions. Once again, you see we're being asked to test a claim, and so this is a hypothesis test. Step 1 is to determine the hypotheses, the null hypothesis and the alternative hypothesis. One of those claims is explicitly stated in the problem. We're being asked to test the claim that the percentage of college students who go to bed with a comfort item is greater than 34%. One of the claims is that the proportion is greater than 0.34. Because that claim is an inequality, that must be the alternative hypothesis. If you know the alternative hypothesis, the null hypothesis is easy to come up with because it has the same parameter, it has the same number, but it's always a statement of equality. So the null hypothesis is the claim that the proportion is equal to 0.34, and the alternative hypothesis is the claim that the proportion is greater than 0.34. Specific to this problem, the null hypothesis is the claim that college students don't really differ from the general population of adults when it comes to sleeping with comfort items, and the alternative hypothesis is the researcher's claim that the percentage is higher for college students than it is for the general population. So we have these two dueling hypotheses. Our second step is to identify the level of significance, which we denote by alpha. Now in this problem, you actually won't see the symbol alpha, but you see that we use the phrase significance level right here, using a significance level of 0.10. That's alpha. Alpha is 10%. Step 3 is to collect the evidence, and when you're testing a proportion, the evidence is the number of observed successes and the sample size. So we had a sample of 50 college students, and 21 of those used a comfort item, and we want to count the ones who used a comfort item as a success because that's the proportion that we're looking at. So X is 21, N is 50. And now what we want to know is, if the null hypothesis was true, how strange would this sample be? Would this be a weird sample? If this is a weird sample, then we don't believe the null hypothesis. And if it's not a really weird sample, then the null hypothesis is plausible. How do we make that determination? Well, we do it with a p-value approach. We're going to calculate the p-value. And the calculator function we use for proportions is 1PropZTest. Press Stat, scroll to Tests, choice 5. P sub 0 is the number on the hypotheses, which is 0.34. X is 21. N is 50. I know I skipped over alpha. Alpha doesn't go into the calculator. We use alpha in the 5th step to help us make the decision. This last input allows you to choose the symbol in the alternative hypothesis. Our claim is that the proportion is greater than 34%, so we want to choose the greater than symbol, which is the last one. So hit enter on that last option. Scroll down to calculate, hit enter. First line you see is the name of the test. Second line should match your alternative hypothesis in meaning. We use the letter P where the calculator uses prop, but it means the same thing. The proportion is greater than 0.34. The next line is the test statistic. We don't really need that. It's this line underneath Z that we want. That's the p-value. The p-value is around 0.116. Underneath that you see p hat and n, but the real reason we ran the calculator function was to get the p-value. We're now ready to make our decision. If the p-value is less than or equal to alpha, we reject the null hypothesis, and if the p-value is greater than alpha, we fail to reject the null hypothesis. Notice that I didn't round our p-value down to 10%. You could round this to 0.1. That would make it look like it's equal, but it's not actually equal. It's greater than. So I gave it a couple more decimal places just to show that difference. The p-value is actually greater than alpha. When the p-value is greater than alpha, we can't reject the null hypothesis. We fail to reject the null hypothesis. This doesn't mean the null hypothesis is true. It just means that it's plausible, it's believable, and so we can't go out on a limb and say that it's false. I want you to notice that the sample evidence still points towards the alternative hypothesis being true. 21 out of 50 is bigger than 34%. But that difference isn't statistically significant enough for us to be sure that the null hypothesis is false, and so we're going to concede and say that we can't reject the null hypothesis. And if you can't reject the null hypothesis, then you can't support the alternative hypothesis, and that's how we write our conclusion. The charge in this problem was to test the claim that the percentage of college students who go to bed with a comfort item is greater than 34%. We cannot support that claim. We're not saying that claim is false, but we also can't say that it's true, and that's how we're going to write our interpretation. I write there is not enough evidence. The common way to make this sound more highbrow is to say there is insufficient evidence. I just say there is not enough evidence to support the claim. What was the claim? That the percentage of college students who go to bed with a comfort item is greater than 34%. I want you to notice how similar that is to the previous interpretation that we wrote when we rejected. Here we said there is enough evidence to support the alternative claim. When you reject the null hypothesis, you do have enough evidence to support the alternative. Think of it this way. You had enough evidence to reject the null, so you have enough evidence to support the alternative. Here we failed to reject the null hypothesis. There was not enough evidence to say that the null was false, and so there's not enough evidence to say that the alternative is true. That is the only difference in the two interpretations. There either is or is not enough evidence to support the alternative hypothesis. I want to point out again that it's incorrect to say that we believe the null is true. The sample evidence doesn't point in the direction of the null hypothesis. 42% isn't equal to 34%. We're not saying that the null hypothesis is true. We're just saying that we're not sure that the alternative hypothesis is true. the null hypothesis is at least believable, and so we're not willing to reject it. Couple more. Baseball was once the most popular spectator sport in the United States, but that's no longer the case. A survey of 1,049 Americans was conducted. Only 92 identified baseball as their favorite sport to watch. Use this data to test the claim that less than 10% of all Americans would choose baseball as their favorite sport. Use alpha equals 0.05. Again, we're being asked to test a claim. So we're going through a hypothesis test scenario. Let's run through our 6 steps. Step 1 is to identify the hypotheses. The claim we're being asked to test is that the percentage of all Americans who would choose baseball as their favorite sport is less than 10%. That has to be the alternative hypothesis because it's an inequality. The null hypothesis is a statement of equality that uses the same parameter and the same number. So the null hypothesis is the claim that exactly 10% of Americans like baseball best, and the alternative hypothesis says no, less than 10% like baseball best. Step 2 is to identify the level of significance, and you can see we just used the alpha notation at the end here. Alpha is 5%, 0.05. We're going to use that to help us make the decision. Step 3 is to collect the evidence, which is the number of observed successes and the number of trials. Back to the problem. There were 92 who identified baseball as their favorite sport to watch. There were 1,049 Americans total. So X is 92 and N is 1,049. A much bigger sample size than in the previous 2 studies that I quoted. But that doesn't guarantee that the results are statistically significant. 92 out of 1,049 is less than 10%. A little bit of number sense tells us that. But it's not a lot less than 10%. But is that difference statistically significant? There's not a big difference between the value of p hat and 10%, but we have a huge sample size. So this is kind of up in the air. That's why we use the p-value to help us make this decision. To get the p-value, we're going to plug in 0.1 for p sub 0, 92 successes, 1,049 trials, and we want to choose the less than symbol, which is the second symbol. We calculate, and we get a p-value of around 0.09. And that's larger than the value of alpha that we were given. Remember, we're comparing the p-value with alpha. The p-value is larger than alpha, and so we fail to reject the null hypothesis. Now, if you're paying attention, you'll notice that the value of alpha has changed in each problem. And if I had set alpha to 10% like I had in the previous problem, then we'd get a completely different decision. There is an ethics involved because you could just pick a value of alpha that makes you reject instead of fail to reject. Because of that, in a lot of real-life studies, they don't actually choose a value of alpha. They just report the p-value and leave it up to the reader to choose a value of alpha. The most common value of alpha is 5%. That's the number a lot of people use as the breaking point between being statistically significant and not being statistically significant. In a classroom setting, you're given a value of alpha and you just run with whatever you're given. The p-value that we calculated is greater than the value of alpha that we were given, and so we can't reject the null hypothesis. And if we can't reject the null hypothesis, then we cannot support the claim in the problem. Yes, the sample had 1,049 people in it, and the sample proportion was less than 10%, but that was not statistically significant enough because it wasn't that far away from 10%. P hat was 8.8%. It was only about 1.2% below the number in the claim. That difference wasn't statistically significant for that sample size. So we can't support the alternative hypothesis. And when you cannot support the alternative hypothesis, you just say so. There is not enough evidence, or there is insufficient evidence to support the claim What was the claim? That less than 10% of all Americans would choose baseball as their favorite sport. I suppose to make this clear, we should make sure to say that this is their favorite spectator sport, not their favorite sport to play. I know that's not how it's worded in the problem, so if you had just copied it, you would get full credit. I can't fault you for that if you just copy the wording in the problem. But if I were writing this for a general audience, I would want to make sure to be clear. And so I would throw in this part about being a spectator sport as opposed to a sport that they participate in. If alpha had been 0.1, we would have rejected the null hypothesis and we would have said there is enough evidence to support the claim. That's the only difference in the two interpretations. You either do have enough evidence to support the alternative hypothesis or you don't. Just like there's only two decisions. You either do reject the null hypothesis or you don't reject the null hypothesis. If you reject the null hypothesis, then you support the alternative. You're getting rid of one hypothesis in favor of another. And if you can't reject the null hypothesis, then you can't support the alternative. You were not able to get rid of the first one, so we can't substitute in the second one. For our last example, I want to do one that uses the other inequality symbol. In the past, 1/3 of all customers at a popular chain restaurant would order an appetizer with their meal. However, the manager at one franchise suspects that trend is changing at her location. A random sample of 82 recent orders reveals that 17 of them had an appetizer on the bill. Does this data support the manager's claim that the proportion of customers who order appetizers is different than it was in the past? Use 0.05 as your significance level. I know this doesn't say test in it like the previous two examples, but we're being asked if we can support a claim using sample data, and so this is a hypothesis test. Step 1 is to determine the hypotheses. The claim we're being asked if we can support is if the proportion of customers who order appetizers is different. It doesn't specify greater than or less than. It just says different. And the symbol we use to indicate that two numbers are different is not equal to. Not equal to doesn't specify greater than or less than. It just says that they're not the same. They're different. The claim is that that proportion is different than what it was in the past, and here we're given the fraction 1/3. So the alternative hypothesis is the claim that the proportion is not equal to 1/3. The null hypothesis would be the claim that it is equal to 1/3. We have these contrasting hypotheses. Notice here we've got a fraction instead of a decimal. That doesn't change the way that we do it. We'll just type 1 divided by 3 in for p sub 0 in the calculator. Step 2 is to identify the level of significance. We're told to use 0.05 as our significance level. That's alpha. Step 3 is to collect the sample evidence, which is x, the number of observed successes, and n, the number of trials or sample size. There were 82 people in the sample, and 17 of them ordered appetizers. 17 out of 82 is different than 1/3. But the question is that difference statistically significant? We have a decent sample size, but it's not enormous like the previous example. So is this statistically significant? So can we jump and say that the proportion of all customers who order appetizers is now different than 1/3, different than what it used to be? This is where the calculator function comes in. We're going to pull up 1PropZTest. So stat, scroll to tests, choice 5. For p sub 0, I'm just going to type in 1 divided by 3 and let the calculator put in a decimal approximation. X is 17. N is 82. We're going to choose the not equal to symbol, which is the first option here. The problem didn't specify whether we were testing for less than or greater than. Real quick, it would be silly to test the greater than hypothesis because 17 out of 82 is definitely less than 1/3. So it would be silly to do the last one. It's reasonable to do the second one, but the claim we were being asked to test is that it's different, and so I'm going to use the not equal to symbol. We scroll down to calculate, and we get a p-value of around 0.015. That p-value is less than the alpha that we were fed, and so we're going to reject the null hypothesis. We're rejecting the claim that the proportion of customers who order appetizers is still 1/3 like it has been previously. We're rejecting the status quo. We now believe that that proportion has changed to something else. And so that's what we're going to conclude. There is enough evidence to support the claim that the proportion of customers who order appetizers is different than it was in the past. You can see I stole most of that wording from the problem. Another way to say this is to just say that it's different than 1/3, which is the historical value. Okay, so we finally got a taste of hypothesis testing. Hopefully this puts some of that abstract stuff from the previous two lectures into context so you can understand what we were talking about. If you have any questions about these hypothesis tests for proportions, get in contact with me.